It's a great pleasure to have as our second speaker of this newly established online LQP colloquium, Horacio Casini, who is a professor at Instituto Balseiro in Bariloche, Argentina, where he's been for many years, but he's also spent time at Princeton, the IIS, Perimeter Institute, and CISA in Italy. In 2015, he was one of the recipients of the New Horizons in Physics Prize, together, among others, with Marina Huerta, with whom he has also written many papers, and he is part of the 8 from Qubit network founded by the Simons Foundation, among other things. It's a great pleasure to have you, Horacio, and it's over to you.
Thank you for the introduction, and thank you, Stefan, and all of you for the invitation to speak today. Well, this is a brief plan of my talk. I will start with an introduction on general features and ideas about entanglement entropy in field theory. The introduction will be from the physics point of view. So I say this because many of you are mathematicians, so don't be alarmed at some of the statements. Then I will start with this idea of a proof of irreversibility of renormalization group using entanglement entropy. And at the end, I will briefly go to this question of interpretation of this irreversibility in terms of quantum information ideas, and some kind of ideas that could be useful to get a mathematical proof. I will talk about this proof of the renormalization, irreversibility of the renormalization group. They are physicist proof too. So let me start. Then I will introduce entanglement entropy. We have a quantum system formed by two subsystems. Here are two spins, and I take, for example, pure state, here an entangled state between these two spins. If I am interested only in the physics in the region or the subsystem A, I can take the trace of the density matrix over the degrees of freedom B and get a density matrix for the subsystem A, which give me the expectation values of all operators there. And with this density matrix, we can produce this functional, that is the von Neumann entropy, and this is the quantity I will be talking about, the von Neumann entropy of a subsystem. In the case that the global state is pure, this entropy can be non-zero in quantum mechanics and not in classical physics, and this is called entanglement entropy in that case, because it measures quantum entanglement between the two subsystems. In general, this entanglement entropy will be a function of the state and the algebra. The algebra A is important here, that the density matrix, even if we get it by tracing out something, is just a functional of the operator expectation values in the region A. So the state in the region or subsystem A. I will be interested in this talk on entropies of extended systems in some subregions of extended systems. But this is the same as to say as the entropy of the operator algebra attached to this region. In this sense, the entanglement entropy is just the entropy of the region. So it's the same idea that was used many years ago, since all times. You compute the entropy of a subregion, and then, for example, you can study the thermodynamic limit of large volume in a thermal state. So there is no new thing. This is the same kind of entropy in the subregion. However, here the emphasis is on a pure global state, especially the vacuum. So there is no volume term here in the entropy. And we are interested in the surface terms. Surface, it depends on the surface, or more importantly, on subleading terms. We will talk about the subleading terms. So it's important that in doing this calculation, we do not impose boundary conditions on this subregion, because otherwise we will spoil the correlation across the boundary that are measured by the entropy that depends only on the theory or the state, for example, and not on arbitrary boundary conditions. So the original motivation for studying entanglement entropy in field theory comes from black hole entropy. From the 70s, we know that black holes in gravity obey thermodynamic laws. There is a first law, a second law, and they have temperature, Hawking temperature. And so they are attached with an entropy which is proportional to the area of the black hole. So from the beginning, the question was what are the microscopical, what is the microscopical origin of this law? How can you understand this in terms of microscopic terms? And one of the nice ideas that people put forth in this to explain this microscopic origin was the idea that it was produced, this entropy, by entanglement across the boundary of the region. So this entanglement is already there. You know that it's there because there are quantum fields, and then they get entangled here in the state that it looks like the vacuum very near the horizon. So one could think that this is producing this entropy, and this has a bonus already because short distance correlations are more important in quantum field theory than large distance correlations. So the entropy will be proportional to something proportional to the area of the region. But there are difficulties in this idea. One is that if you have a quantum field theory in fixed space-time, you get infinite divergent entropy because of ultraviolet correlations that are piled up along the surface. So you need the quantum gravity to regularize that to get a final result. We have a finite number here in the entropy of the black hole. And the other problem is that once you put quantum gravity, the idea of having a region and an algebra attached to it is shaky, because what is really the region where this algebra is attached, for example, if the geometry is fluctuating. So there are these problems with this. But in 2006, Ryu and Taganyagi proposed the following idea that is called an holographic entanglement entropy, that gives a modern perspective to the black hole entropy. This holds only for holographic theories that are theories that live in asymptotically ADS spacetime. So we have, for example, here the bulk of the spacetime, which is asymptotically ADS. And here we have a quantum gravity theory. And this is dual to a boundary theory, which is an ordinary quantum field theory. And what they proposed was that if you take a region in the boundary theory, the entanglement entropy of this region is given by the minimal area that ends on the same boundary, the minimal area on the bulk, divided by 4G. So it's the same formula as the black hole entropy. And this idea gives an interpretation of black hole entropy as entanglement entropy, but not just entanglement entropy across the horizon, but it's entanglement entropy in the boundary theory, in the quantum field theory. So for example, here would be the area of a black hole would be the entanglement entropy between the full boundary and some other asymptotic boundary that you get crossing the black hole. But you get a large generalization of the black hole entropy formula in this way. It gives you the entanglement entropy of any region in the holographic theory. And there is no problem with the algebras now, because the algebras are really algebras of quantum field theory. They are attached to the boundary. So from the mathematical point of view, you have an algebra there. It doesn't suffer from the problem of trying to define the entropy of some region in the bulk. The entropy, the density of entropy is finite here in the black hole. There is no divergences. Though the entropy of a region like this B is still divergent. The entropy in the quantum field theory is divergent because the area gets infinity as you go to the boundary for hyperbolic space. The proof given by Legois and Maldacena of this formula is rather thermodynamical in a sense. So it doesn't give an understanding of the microscopic origin. So we lost this idea of the microscopic origin across the boundary in the bulk. It gives the entanglement in the boundary, that is a non-local quantity, as something that is localized in a surface in the bulk. We do not understand very well how this happens. So, but then, as black hole entropy is just entropy in a quantum field theory, let us look at more closely what happens in the quantum field theory. So in the quantum field theory, entanglement entropy is a nice dimensionless quantity labeled by the geometry of a region, for example. It can be defined for any theory. So it has quite nice features, and one would like to understand it better. There is a problem, of course, that I have already told, that this quantity is divergent, right? So we need, in principle, to regularize it. For example, here I'm putting a circle in a square lattice for a free massless scalar. What we expect is that the entropy has in this case, an area, in this case, perimeter term, divergent. This epsilon is the lattice spacing, something like that, some cutoff. And then you have a subleading term that is a constant, that is the F term here is called, that you suppose that this is well-defined. But just to check it, if it is well-defined, you can put it in a square lattice. For a circle is very bad choice, of course. But then you compute the entropy and it grows linearly, so it has the area term, but it has a lot of fluctuations. And if you subtract the linear term to get the finite piece, you get this. You get, it never ends as you increase the radius. Increasing the radius means also decreasing the size of the lattice, so you go to the continuum limit, it doesn't converge. So what happens? How can one extract an ambiguous information from the finite terms? One way to do that, would be to choose a better cutoff, let's say. But one universal way to do that is to compute this other quantity, this mutual information, that is combination of entropies. So for example, for two regions is the entropy of one region plus the entropy of the other minus the entropy of the two together. And in this way, you eliminate the divergent pieces because the cutoff dependent terms are always local and extensive on the boundary. So we are like integrals on the boundary because they come from ultraviolet physics, short distance correlation across the boundary. So as the boundary in some point appears in the region A and in the union, they get canceled here and you expect a finite result. And in fact, you can check in the lattice that you converge to something even in taking circles, for example. And it's also true that this quantity, because it's a special kind of relative entropy, can be defined also in the continuum itself without any cutoff through the hierarchy formula for relative entropy. So it coincides with this idea, this more naive idea in quantum field theory. So once you have this mutual information, you can try to write an entropy for a fixed region here, just regularizing geometrically, taking two boundaries very near to the surface you are interested in, and computing the mutual information divided by 2, and you expect this to get to give you a universal regularization of the entropy, and you can extract from there the constant term for example, for this free scalar, I give you this number. In the lattice, you can take some numbers here. And it also coincides with some other analytical calculations using some other tools. So, how do information measures fit in the general scheme of quantum field theory? This is kind of an ideological transparency. So we have this formulation of quantum field theory, for example, in terms of fields, and we know that taking vacuum expectation values, we have these correlation functions, and the theory can be reconstructed from the correlation function. So you take operators and obtain numbers, and then you describe the theory just using numbers. So, and there is also this other formulation, the algebraic quantum field theory, which is based on the algebras attached to regions in space-time. It's a kind of basis-independent formulation because it doesn't depend on the particular fields you take to generate the algebras. So how can you attach a number like this step? How can you attach a number to an algebra? If you think a little bit about that, the only thing that you can produce is out of the vacuum or some other state, you can produce statistical properties. So entanglement entropy, mutual information, range entropies, etc. You can study those. So one would like to understand if, for example, with the set of mutual information, one can reconstruct the theory, but we are very far from that. But it seems that at least the mutual information contains all the information of the theory. It's so uniquely defined the theory. For example, for conformal field theories, the relevant data, the conformal dimensions, the three-point function constants can be in principle be extracted by looking at the mutual information in an expansion for large distances. So even if the information is there, we do not know of a complete set of axioms for mutual information in quantum field theory yet. So let me then enter into the main theme of this talk, that is an application of entanglement entropy to the irreversibility of the Romanization group. So the Romanization group describes the change of the physics in a quantum field theory with a scale. You think you have a theory like, for example, the standard model, and if you look at the physics at short distances, you see there are a lot of like massless particles, quarks, gluons, photons, electrons. If you look at the large distances, all of these fields become massive, and you only get the photon. There is only the photon with zero mass. So the idea is that you start in the ultraviolet with some fixed point that we assume is a conformal fixed point. And at the infrared, at large distances, the theory approaches some other fixed point that is the infrared fixed point. And you can describe that perturbatively just as a movement with the scale of the coupling constants. But in this talk, I will talk only about other things, not about the coupling constants. So the idea of the reversibility of the Romanization group is the idea that there is an ordering of the fixed point. For example, if you start in ultraviolet with some CFT1, conformal field theory 1, and you go to conformal field theory 2 at the infrared, you cannot go in the other way, from the 2 to the 1. So in order to prove this, you need to test the Romanization group non-perturbatively. And you need also a quantity that is always, like, say, decreasing along the flow that is defined for all theories, or at least for a large set of theories. There have been several proofs of these irreversibility theorems along the years, not using entanglement entropy. The first one was some homological proof in 2 dimensions that uses correlator of stress tensors. the more recent one by Komorowski and Schwimmer uses for 4 dimensions, uses the effective action of the dilaton. So this is a little bit less applicable to axiomatic schemes. And for dimension 3, there was a proposal and a proof by Myers and Sinha only for holographic theories. So it's a kind of gravity proof. So here we will use entanglement entropy. And with this entanglement entropy, we will compare some quantity that appears in entanglement entropy in ultraviolet and infrared and see how this changes. And it's a nice thing that already in the entanglement entropy for spheres in a conformal field theory, the quantity that these people have thought that is irreversible appears in the spheres in a conformal field theory. For example, here are in dimension 2, you have for an interval, the entropy grows logarithmically with the size, and the coefficient is the Virasoro central charge of the conformal fixed point. In dimension 3, you have an area term or perimeter term and a constant term. So this will be the monotonic quantity, this F. In dimension 4, for a sphere, you have an area term and then you have a logarithmic term, again, as in 2 dimensions. In all even dimensions, there are logarithmic terms. And this A is the quantity that is monotonous. So this is why these theorems in these dimensions are called C, F, and A theorems. In even dimensions, the relevant quantity A and C are trace anomaly coefficients. It means that they can be extracted from stress tensor correlators. But in dimension 3, this quantity F is a very non-local quantity. It cannot be extracted from correlators. It contains information, for example, it contains a topological entanglement entropy for topological theories. So the entropic proof that I will show is very simple and geometrical. And we need, and it's given in these several papers. I will show you, the last picture we have of this, that is by these papers. And I have to warn you that when we started with this with Marina Huerta, we made a proof in 2 dimensions, and we said with the same method, you cannot prove it in higher dimensions. Later, we proved it in 3 dimensions with the same method and said you cannot prove it in 4 dimensions or higher with the same method. And then I will show you here that with the same ideas, you can prove it in 4 dimensions, but we still say you cannot do it in higher dimensions. But I hope I can convince you, because we now have a more clear picture that these theorems say the same thing in all dimensions, and why it cannot be used in higher dimensions with the same ideas. So we need 3 properties. We will assume at some point a covariant cutoff. Later, perhaps I could talk more about this, but it's expected that you can produce a covariant cutoff using mutual information, as I described before. But we need other 3 properties. One is the Poincaré invariance in vacuum. The next one, I call it causality. Maybe you can call it different ways, but the idea is that even if we think on a lattice of spins or whatever, the entropy is not a function of this surface in space-time, but it's a function of the causal diamond or the causally complete region, because the algebra where you compute the entropy is attached to this diamond. So it's a function of diamond-shaped sets. And the third, of course, we need, in order to prove some monotonicity, we need an inequality, and we'll use this strong subadditivity property that here has this form. We have 2 regions. The entropy of one region plus the entropy of the other is greater or equal than the entropy of the intersection plus the entropy of the union of the regions. So this property cannot be used for any region in space-time. They have to lie in the same Cauchy surface. So they have to, in this case, for example, they have to cross if they are slanting in space-time. So it's important that the boundary, are the boundaries of the region. The boundaries determine the causal domain of dependence. So we will talk more about the boundaries because they are just labeled the causal domain of dependence. The boundaries have to cross each other in this situation. And this inequality is very important in quantum information theory. It's related to monotonicity of relative entropy, somehow the loss of information in quartz graining. And the second law, when the second law can be proved, that this you have to assume some things and then you can prove it. Of course, it's a proof under assumptions that are not always there. Well, let us start giving the main ideas of this proof. A preliminary observation is the following. If the strong subadditivity property that I shown here is going to say something interesting about the Romanization group flow, it must be the case that the inequality is saturated for a conformal field theory. Because in the conformal field theory, you don't have a Romanization group flow. The quantity that is monotonic has to be constant. So we need the inequality is an equality for a conformal field theory. So then one can ask, when is possible that this inequality saturates? It's just an equality to zero. And this is in the literature is called, when this happens, the state where this happens is called a Markov state. So it's kind of a generalization of a Markov change. I will not talk about that, but this is the origin of the name. One important consequence of this Markov property that, as you see, is a saturation of an inequality, so it's very strong, is that if you have this situation, then if the state is Markovian, it means that region 1, so this is the region 1 is that the exclusive part of A, and region 3 is the exclusive part of B. Between region 1 and region 3, there cannot be quantum entanglement. There can be classical correlation, but not quantum entanglement. However, this is in general impossible in quantum field theory due to Reed-Slider theorem. So let us see how this happened. The Reed-Slider theorem tells you if you have a region with a space-time volume and you take the fields in the region and acting on the vacuum, it will generate a dense set of states in Hilbert space. And the proof uses an analyticity of the correlators in this region and needs this has a space-time volume. And then it happens that the Reed-Slider property implies that, for example, in this situation, I'm drawing now picture in space-time, these diamonds. So this is intersection, and this is our region 1 and 3, that exclusive parts. It happens that there should be some quantum entanglement between region 1 and 3. This is because doing operations in the vacuum in the region 1, one can produce with perhaps a very small probability an EPR pair between 1 and 3. So there is something that is called distillable entanglement. It means that the state cannot be Markovian. The strong subadditivity cannot saturate in this situation. So what can we do? The only possibility is then that regions 1 and 3 do not have a space-time volume to bypass Reed-Slider theorem. And this is the situation. For example, I take region A and region B, such a way that the exclusive part is just a null surface. Then it's a piece of a null surface. Here there is another picture where I draw boundaries on a null cone, And then in that case, again, the exclusive part is just a null surface. In general, one can check that this is not enough. So in general, even if this is a null surface, strong subadditivity will not saturate. I will show a case where it does saturate. Just a remark here is that in general, this region 1 and 3, for example, for interacting ultraviolet fixed point, do not have an algebra attached. So there is no space to smear the fields there. They do have an algebra for free fields, but in general, no. But even if they do not have an algebra, this region A and region B, the intersection is this region, is this algebra 2, which is not equal to A or to B. So how we prove? We will show that the Markovian property is expected for regions like this. So this is like a Rindle wedge. So the boundary lies in a null surface, but is the form. It's like the form Rindler wedge along a null surface. For this type of regions, you will have, in any quantum field theory, you will have like a Markov property, and this is like a short physicist proof. You take regularized entropy, Lorenz covariant regularization, in such a way that if you do a boost, the boost acts on the null lines like a dilatation, like a scaling. So if you make a boost, for example, you can make this surface to shrink to this line in the limit of large of a small lambda. You can shrink to this line. So it means that all these curves that you can draw there will go with the same entropy, will go to this Rindler case. So it means that the entropy really do not depend on the shape of the curve. Once you have that, you can play this game. You can do strong subadditivity for regions with boundary in the null plane, and it has to cancel because all of the pieces here have the same entropy. But now we can lift the Lorenz covariant cutoff because the contributions of the regularization are local and extensive on the boundary. So this combination is cutoff independent. So Markov property is really cutoff independent. As I have shown, this property is you see here, there is nothing about the entropy. So it's a property of functionals, of curves in of Lorenz invariant functionals of surfaces, right? So there is it's very geometrical, and there is nothing about the entropy. It also holds for other things, expectation value of non-local operators or the range entropies, etc. But speaking about the entropy, it roughly tells you in a naive way that the state on these null surfaces is kind of a product state along for different null lines. So it's like the state is a product state. For a free theory, this is correct. Of course, for for interacting theories, this is just a naive understanding. So somehow it's a kind of result opposite, in the opposite direction of Freer-Leider theorem, because it tell you that in some particular like geometry, like this plane, the vacuum state looks like the couple between the different null lines. So this is a side remark because I will not talk much about this in the talk. The Markov property is very strong. In fact, this equality of the entropies implies, in the finite case, at least, that the same combinations of operators these operators are the modular Hamiltonians of the different regions. The same combination of the modular Hamiltonians are equal to 0. For people that do not know what is the modular Hamiltonian, here we can think the modular Hamiltonian is just the logarithm of the density matrix. You have this property. So, and you can think what can happen to produce this. And it is the fact that you can think these modular Hamiltonians for these curves acting or on each null line separately, independently. It's the same idea as that the state is a product state for different null lines. With this modular Hamiltonian, you can produce the modular flow that are exponentials of the modular Hamiltonian. And this modular flow, this unitary flow, will act independently on each of the null lines. And as it acts independently, it means that they act in the same way as the Rindler case, where we know exactly how it acts. For example, for this curve gamma 2, it will move other points or regions or algebras in this null line in the same way as Rindler wedge based on the same point there. And from this idea, you get that modular Hamiltonians commute. The commutation relation is the same as the Rindler modular Hamiltonian, which is just a boost on each line independently. And this is related, I will not have time to enter into this. This is related to half-sided modular inclusions. Another remark is that these unitary modular flows for these regions here in the null plane act locally on other algebras that are located also in the null plane, the boundaries. But the action of these null modular flows is non-local outside the null plane, except in the case of Rindler wedge, which is a Bissonian-Wicherman result that it acts like a boost everywhere, or in the case of spheres that is a Hislop and Longo result. In a CFT, it's also acting locally everywhere. So once we have this Markov property on the null plane for any quantum field theory, if we take especially a conformal field theory, we can conformally map this to a null cone, and we have a Markov property for regions with boundary in the null cone. Another side remark is that for regions with boundary in the null cone, we have this idea of the Markov property tells you the general form of the entanglement entropy as a function of the curve. And this is based on two ideas. The first is that the entropy, because it has to satisfy the Markov property, has to be like a local functional along the angular directions. It's a local functional of the curve. So it looks like an action. It looks like an action depending on this gamma, on this curve. That's a function of the angle. And there is also Lorenz invariance. If you apply a boost here, it will also get to the same null cone. And Lorenz invariance, if you look at in terms of the coordinates on the angular coordinates, it acts as a conformal transformation on the unity sphere. So you have something that some local action or conformal invariant, and this parameter transform, which is the logarithm of the size here, transform as a dilaton. And this problem of producing local actions which are conformal invariant for a dilaton have been studied in the literature, and you get these results. For example, in 3 dimensions, the entanglement entropy for any of these curves is just has an area term, but the F term, the constant term, is always the same for any curve. And in 4 dimensions, you get also an area term, you get a logarithmic term with a coefficient a, but this logarithmic term has to be together with this term that depends on derivatives of the curve in such a way that this is Lorenz invariant. So let us come to the main point there, then, that that we wanted a case where strong subadditivity saturates in a conformal field theory, and this happens in the cone, in the null cone, for regions with boundary in the null cone. So then we have to try the strong subadditivity inequality for theories which have scales, which doesn't have which are not conformal field theories. In that case, the inequality will not saturate. So as we want to produce a result for spheres where there are these coefficients that are supposed to be monotonic with the size, we need an inequality for spheres, and we can take, for example, here, I draw a boosted sphere that will boundary in the null cone. But if you take two of these spheres, the intersection and the union will not be spheres, so we need to use many of these boosted rotated spheres and apply strong subadditivity many times. If you apply strong subadditivity many times, you get on one side the entropy of these boosted spheres that are rotated, so they are all equal. On the other side of the inequality, you get the entropies of different regions that look like this black white region that I draw here. They look like what we call wiggly spheres. They are going around some green like a sphere here, but they have wiggles. And the size of the wiggles and the number of the wiggles increase as you take more n larger and larger. When n goes to infinity, you expect that these wiggles go to zero size. Still, the slope is not getting zero, but you get many wiggles with a very small size. If you take this limit, you get something like this. The entropy of the original boosted and rotated sphere is greater or equal than some integral of some numerical constant and some wiggly spheres for different sizes. So this is pure geometry, pure Minkowski geometry. You don't need to take care about that. And then the question is whether you can replace in this inequality the wiggly spheres by spheres in the limit. From the physicist point of view, of course, you can replace it. You can, at least your first intention will be to replace it. So let us do that. We replace the wiggly spheres by spheres in the limit, and then we get an equality only for the spheres. You can take here the limit where these two numbers are near to each other, and then this gets into a differential inequality, this one, that depends on the radius. This is just an inequality for derivatives of the entropy as a function of the radius. So let us check it for a conformal field theory. It should be the case that as this comes from strong subadditivity, it should saturate, right? So we take the two-dimensional case and it saturates. It's natural because there are no wiggles in 2 dimensions, there are just intervals, and there's no these wiggles. In 3 dimensions, it saturates too. And one can argue that the wiggles do not contribute in the limit of a small wiggle. But in 4 dimensions, if you apply this inequality, you get something that is positive. It doesn't saturate. In fact, it gets the wrong sign, So what is happening? What is happening, of course, is that this step of going from wiggly sphere to sphere is not justified. And the reason is this term. This is the entropy for arbitrary regions of the null cone. So this term will get finite contribution even if the wiggles go to 0, but the slope is non-zero. So in order to remedy that, you can actually compute this and add it to the inequality, or better, you can just use the Markov property again. Instead of talking about the entropy of your quantum field theory with scales, you can talk about the entropy of the theory with scales, subtracted the entropy of the theory in the ultraviolet fixed point. Because this one satisfies Markov property, it doesn't spoil your inequality. And then the subtraction is does not contain this term, and then you can smooth your wiggles in the limit of a small wiggle and obtain this inequality for spheres. Now, this is for spheres, not wiggle spheres. You can also write this in terms of, instead of writing in terms of radius, in terms of the area of the sphere, and it gets this simple formula that the difference of entropies as a function of the area is concave for any dimension. So what it tells about the reversibility theorems. Once we have this inequality, we can check what happens for the difference of entropies in the ultraviolet and infrared. In the ultraviolet, because it's subtracted from the ultraviolet fixed point, you will get 0, and in the infrared, you will get an expansion. There is an expansion with the area term, and this is just how the area term renormalizes as you go from a smaller sphere to larger spheres. You have a subleading term, etc. And at the end, you have the terms with dimensionless coefficients, which involve difference of coefficients between the infrared and the ultraviolet conformal field theories. This is for even dimensions, and this is for odd dimensions. And the theorem tells two different things. One, the inequality tells two different things. The first is that the area term always renormalizes negatively. If you apply it to 2 dimensions, in 2 dimensions, the area term is just a logarithmic term, it's just the most important term. And it tells you that the coefficient of the logarithm, in that case, is just the Virasoro central charge decreases, and this is the C theorem. And for dimension greater than 2, it tells that the area, what we call the area term, that the coefficient of the area term decreases towards the infrared. And the other thing that it tells is that the second coefficient, the subleading coefficient here, renormalizes positively, and this applied to 3 dimensions give you the F theorem, and applied to 4 dimensions give you the A theorem. So we can see here that the theorem tells the same story in any dimensions, but it only reaches the dimensionless coefficients, CFT coefficients, that are the last ones in the expansion of the entropy of the spheres, only for dimension 2, 3, and 4. In higher dimensions, you will get some inequality, these 2 inequalities that involve changes of constants in the expansion of the entropy that are dimensionful, like the area, for example, coefficient in dimension higher than 2. So it has information of the Romanization group flow, the constant, as it is a dimensionful quantity, it has to be dependent on the parameters of the Romanization group flow and not on the conformal field theories itself of the fixed points. So, but this proof based on entanglement entropy unifies all known irreversibility theorems. And it's the only general proof in dimension 3, which is entropic. And one can think it's difficult to produce a proof without something like this, some tool like the entropy, because it's, as I already mentioned, this F quantity is quite non-local. And another commentary is that the area theorem, this changing of the area term, is consistent with the sign and also with the amount of the running of the Newton constant when one integrates out quantum field theory effects. So the running of the Newton constant when you integrate out quantum fields give you exactly the same change as the area coefficient for the entanglement entropy, what is consistent with the fact that the Newton constant appear in the black hole entropy formula. So one question here is how to reach to the dimensionless coefficient for dimension greater than 4. So how to produce a irreversibility theorem for higher dimensions. We do not know if there is a theorem like that, but if that would be the case, it seems that more inequalities, and still talking about the entropy, it seems that more inequalities involving more regions seem to be needed. So inequalities farther than the strong subadditivity that involves only 2 regions, because with more regions, you can take the infinitesimal limit and of the deviations and get inequalities for higher derivatives, and higher derivatives can kill these unwanted terms and reach to the universal parts. But of course, we do not know of any inequality of this type yet. So let me then enter into this interpretation. What is the interpretation of this irreversibility of the normalization group flow? So what is lost along the normalization group flow? From the beginning of homological theorem, people have thought about these type of things, and the idea was somehow that what is lost is somehow the number of degrees of freedom. If you have a massless fields that look like massless in the ultraviolet for short distances, when you go to large distances, these massive fields get decoupled, and then you lost along the normalization group flow some fields. But it's a difficult idea to make more concrete or more precise. In particular, because the degrees of freedom in the quantum field theory are always infinity. So it's something different going on, in fact. But one can expect naturally that once you have a theorem based on entanglement entropy, because of the entropy has this quantum information interpretation, one can understand better what is happening. Still, even if we have a proof based on entanglement entropy, we still do not understand quantum information meaning well of these theorems. But one idea is the following by due to Lascari, is that it's about this question. We have this strong subadditivity that I used to prove the theorem. This is in 2 dimensions. You have these 2 regions whose intersection is the region 2, and the union is the region 1, 2, 3. And you can see that this, because of Minkowski geometry, you can take these slanted or boosted intervals, very small in size, very small in real distance, and this intersection will be also very small, while this union can be very large. So the question is whether you can reconstruct the state in the large region based on the knowledge of the state in these boosted small regions. And it turns out that for a conformal field theory, you can do that because it's just a consequence of the Markov property. Another consequence of the Markov property is this one, that for example, thinking in finite terms, the density matrix in this large region is just computable from the density matrices in the smaller regions using this equation. It's exponential of the sum of the say, Modal Hamiltonian of these two regions minus the one of the intersection. The problem is that, at least what people in quantum information theory say, that you cannot reconstruct exactly as an state when strong subadditivity is not saturated. So somehow, what this interpretation tells us is that what is measuring this Romanization group irreversibility is the failure of reconstructing a large state for a large region in terms of the states for smaller regions. But still, we do not understand how to produce of this idea of reconstruction some quantity that can be used for measuring how the Romanization group flow is irreversible. But still, it's very different from this idea of the number of degrees of freedom. It's quite different. Especially, for example, in 3 dimensions, the quantity F is the topological entanglement entropy that is non-zero for even for a theory which one could say, well, it doesn't have any degrees of freedom locally. So this last transparency is about some ideas on how this physicist proof that I shown could be in principle make more rigorous. So an idea for kind of a mathematical proof. The first idea is somehow the same path that I have described is using the mutual information. Suppose we have some region and we want to define a finite entropy, then we can take the mutual information between the outside and the inside, but separated by a small distance, distant cutoff, that has also some direction. This vector n eta, sorry, is some direction on this framing. This is called a framing, separating the two boundaries. And then one can compute the regularization, just the mutual information divided by 2. And then the idea would be that this quantity, this mutual information, in the limit of a small epsilon, now the theory is in the continuum itself. There is no cutoff. It's just a distance, a physical distance that we take very small. And then we could in principle expand the mutual information in terms that depend on the framing, depend on epsilon and the vector eta, and terms that do not depend on that. And the terms that depend on the cutoff should be local, should be something local and extensive along the boundary. And then we can just subtract this term to get a finite quantity. And this finite quantity should be now Lorenz invariant because it doesn't depend on the framing. The framing has been subtracted. It can, as it's a subtraction, in many cases, this finite quantity would be negative, for example, but doesn't matter. And another thing that one could expect to retain for this regularized entropy is a strong subadditivity. Why is that? Because what we have subtracted is local and extensive. So once we prove this, if one could prove this, then all the rest of the theorem is mainly geometry, so it doesn't, it's already done, let's say, somehow. But this thing, we do not know. We expect that this thing is correct, but mathematically it would be tough to prove, I don't know. And another way, perhaps, to go to this idea is using the relative entropy between the vacuum of the theory and the vacuum of the ultraviolet conformal fixed point. So this is suggested by the proof itself because because these quantities, this difference of entropies that I shown you, used between the entropy of the theory and the entropy of the ultraviolet fixed point on the null cone satisfy this inequality. But you can also see that because the state or the reference state that is a vacuum of the conformal field theory satisfies the Markov property, then you can convert this inequality into inequality for the relative entropies. So this combination is exactly the same as this combination of relative entropies. You can complete this to obtain the relative entropies. And this is expected to have a definite sign. And this inequality is called the strong superadditivity of the relative entropy in the case that the reference state, this rho zero, is Markovian. So perhaps one can define these relative entropies, what doesn't seem to be easy. Perhaps they are not well defined, these relative entropies, but there is a well-defined notion of this combination. Well, I think I have finished.
Okay, thank you very much.
Thank you.
Okay, are there any questions for Horacio? You can type them in the chat or, or turn on your microphone.
Can I ask a very basic question?
Yeah, sure.
Because I once tried to read this work from the 70s about the thermodynamics of black holes, and I really don't understand what these laws of thermodynamics of black holes should work that way, because I just don't feel convinced by these arguments, since we don't, I think, still don't have any experiment of entropy of black hole. Can you say how is your perspective on this?
Okay, of course, we don't have experiments yet. Let's say yet. Well, for many years, perhaps. But still, there are many like theoretical ideas. So
can you speak louder, because I have a quite.
What I say is that well, let me see, all these ideas, the first law, the second law, are just classical gravities, for example, classical gravity theorems. So it depends on just Einstein equations. You can prove them. So they look like, for example, the second law will tell you that the area of the horizon always increases. And then, for example, people, well, Hawking demonstrated that if you include quantum fields in the background, the black hole actually radiates at a specific temperature. And now we have also proofs of the second law, also including the quantum fields in the background in the semi-classical limit. So this depends on the monotonicity of relative entropy, for example. So this is the basis of this conjecture, that is the entropy. The black holes are thermal objects with an entropy, associated entropy. Yes.
Okay, this is answer to my question, because I believe, because I can do such many computations in short time, that what you say is very sound approach if we consider this conjecture as true. But it's always bugging me in this problem of entropy of black holes, since is you know, the theory is good, but you can always have a doubt without experiment, in my opinion. Thank you very much.
Okay,
Yeah,
are there
yeah.
any other questions to Horacio?
May I ask a question?
Yes.
There is a rigorous work on the scaling algebras by Buchholz and Ferch. I wonder whether you have tried to use that work in the Theorem, for example.
No, I know the paper. I have started reading it sometimes, but I haven't get into deep into that. Yes, it would be nice to look at this idea of how I think they define somehow a renormalization group flow like in a mathematical rigorous fashion, right? Not using coupling constants or that.
Yes, yes. So it looks natural to look at that.
Yeah, yeah, sure.
Okay, further questions? If you'd like to write them in the chat, that's all right as well.
Sorry, I have a question. So I was wondering whether the Markov property is true for more general quantum states. For example, a global thermal state, is it true for such states?
Sorry, you said global?
Yeah, so like if we have a global thermal state, then is this Markov
No.
property satisfied?
No, it doesn't. It doesn't hold. No, no.
Okay.
It really needs Lorenz invariance of the state. Yeah.
So is it true for only true for any Lorenz invariant state?
At least it is true for a Lorenz invariant state. Yes.
Okay.
And we have only the vacuum, I guess.
Yeah.
But it can be true. I think it can be true. Let me remember. For example, if you take, let me see, if you take the vacuum and then just apply a unitary inside the intersection, for example, then it will change. The unitary will not change the entropy. So let me. So for example, let me this case, right? If I take the vacuum, then it holds the Strong's the Markov property, and they apply a unitary that is located inside the intersection of A and B in the bulk, right? So right. Then it doesn't change any of the entropies, and it's still Markovian.
Okay, thank you.
Other questions?
So yeah, I would like to ask a question that maybe sort of pulls back on this first question that was asked. Sorry, I will admit that my string theory knowledge is not is quite basic. But what always confuses me is when people talk about entanglement entropy across the horizon. They usually only consider matter fields, but obviously in quantum gravity, there are also that you would also expect some gravitational entanglements across this horizon. Is this also counted into this entanglement entropy idea, or is this more of a semantic?
Yeah. Okay.
Semantic point.
It's an interesting question. You have for the general formula, you have, for example, you have this region in the quantum field theory, and you have the minimal surface in the bulk, or some region that will capture the horizon of the black hole, right? And this contribution that is a minimal area over 4G is the contribution of just the part that we do not understand well. It's the part of the, as you say, the gravity part. The contribution of the quantum fields in the bulk, you have to add it here. So there is another contribution. This is like, look at this is the main contribution in the limit of a small gravitational constant. So in the semi-classical small gravity limit, this is a main contribution. And it also, from the point of view of the boundary theory, it's the contribution that grows, for example, with the number of degrees of freedom. This also always holds for large N theory, so it grows with the number of degrees of freedom. And you see that the entropy grows with 1/g. It has to be large entropy. The boundary theory has to have a lot of degrees of freedom in order to be holographic. So this contribution captures the leading term in the number of degrees of freedom. But then there are other contributions that are subleading in the number of degrees of freedom or subleading in the Newton constant. And these contributions can be computed by computing in the semi-classical bulk the entanglement entropy across the minimal surface, across the horizon, across the minimal surface. There you have still the divergences of the entanglement entropy of the quantum field, but they are supposed to be renormalized in the Newton constant. So in the Newton constant of the leading order.
Okay, thank you.
Okay, more questions?
I have one question. You mentioned that the possible interpretation of what is lost along an energy flow is that you lose the ability to reconstruct a state from some region given some other region, right?
Yes.
So is this something then that you can connect to maybe more quantum information notions like recovery channels and quantum error correction?
Yeah, exactly. Well, I would like to understand this better, but people have talked about recovery channels. So in this case, so it's an operation that you do in order to recover some state. In this case, with the knowledge of these states, with the knowledge of rho 1, 2, rho 2, 3, and rho 2, if you have Markovianity, you can recover exactly the full state. But in general, the recovery is not precise, so it has some errors. And as I understand, there is also not preferred recovery map, or there are like several possibilities. So, but still, one could try to understand these recovery maps, choose one of them, and see if the amount that it fails to recover in the case of you don't have a strong subadditivity saturation is related to the change in the central charges or whatever. But I think this is not done yet.
Okay, thank you.
Okay, so any other questions? If not, then maybe I'll have one last question. We could
Sorry, may I have a question?
Sure, yeah.
So on your last slide, you talk about this mutual information regularization, and you said about if you subtract, it could be you subtract the local divergent terms, you're going to get a negative number. So this reminds me of, like in information theory, there's this sort of modification of the Shannon's original idea of differential entropy, so-called the limiting density of discrete points, is sort of invented by Edwin Jennings, and it's like he gave a version of how to define a Shannon entropy for continuous distributions, and there is also you can subtract the boring divergent terms, and you have some negative entropy. Are they somehow formally related? Have you thought about this?
You mean the entropy for classical continuum variables? You mean that?
Right, right.
Okay, well, this is again, this is somehow another way in which the entropy can be divergent. You have a classical system and you get the continuum limit, and then you get this. Probably they are related in the sense that if you think defining an entropy in this way, maybe you have to use some relative entropy or something like that in order to regularize that, right? Or something.
Mm-hmm.
So the relative entropy in the classical continuum variables is still well defined, and then perhaps if you compare with some fixed state, you can define kind of an entropy for continuum variables or something like that. Well, in that sense, it looks like similar in the sense that here I'm using the mutual information, but
Okay.
Not exactly the same. Yeah.
Okay. Thanks. Yeah.
Okay. I think there's one remark in the chat. Maybe this was in response to the previous question, possibly. So I don't take this as a new question. So perhaps one last question in your ideological slide, Horacio. You pointed out that you need a map from algebras in states to numbers, and
right.
There is, of course, the scattering matrix, as you know, Haag and Well showed a while ago, in the 50s, 60s, that this is also an invariant in the sense that it doesn't depend on the chosen generators and the chosen fields, favorable circumstances. So is there a way to relate the scattering matrix to other types of entropic quantities, like maybe associated with null cones or forward light cones? Have you ever thought about that?
No, not really. The thing that I know that people have thought about is somehow if you have a free theory, you can think in the entanglement entropy in a sector of the Fock space in momentum space. And for a free theory, this is 0 in the vacuum. So you have a kind of product state there. So if you have a kind of two asymptotic like free states, free theories that are like in and out Hilbert spaces, you can think about something related to the entropy in momentum space, let's say, for the in and out states, or how they are related. But this is the only thing that I know that people have thought about.
So one would still have to compute the in and out states, and then
sure, yeah.
Then one can just as well compute the amplitude. It's also an answer.
Yeah, exactly. Or unless you have a new tool coming from this, but
Okay, well, as this has been going on for 20 minutes or so now, I think it's time to go for tea or Coke or coffee or whichever your favorite drink, or whiskey. Perhaps not this time of the day yet. Horacio, thank you very much again. I will send you a drink by mail.
okay.
You have to tell me what is your favorite one as your honorarium for giving this very nice colloquium, and thanks to all for coming.
Okay. Thank you, Stefan. Thank you all. See you.
See you. Bye-bye.
Bye.
Oh, sorry. Yeah.
All right, so let me know what you want to drink, Horacio.